So thanks, everybody. My name is Simon. Welcome to the talk, Model Composition with Shared Deployment Graph. I'm a software engineer at Anyscale, and I lead the RayServe team. And in particular, what we're going to do today is going to be, I'm going to give you a slow introduction about what is RayServe, what problem do we solve, where do we stand sort of in the model serving landscape. And then I'll talk a little bit about the context and motivation for us to build a brand new API, as well as go over a little bit of deep dive into what the API looks like in the new generation for us to optimize for the inference graph multi-model serving scenario. And then I'm going to give you a preview of what's coming up with RayServe deployment graph. Cool. Let's start with what is RayServe. So RayServe is part of Ray AI Runtime. You have heard a lot about today, announced in the keynote. So in particular, RayServe is a component in our Ray AI Runtime that's responsible for online inference. And by online inference, I mean this kind of, once you have trained a model, you want to put it in production for live interactive querying, that where you have this kind of low latency, high throughput kind of target. You want the response to be delivered almost instantly. So RayServe in general is a framework optimized for flexible, scalable, and efficient online inference. And by building on top of a common ground Ray, we have all the scalability benefits, also have the low latency RPC call inherited from Ray, as well as the efficiency, where you're going to see a lot later, where you can pack a lot of model into same set of hardware to improve utilization and save cost. And we actually also have first-class support for multi-model inference. And by multi-model inference, I mean the cases where you are forming a sequential pipeline with pre-processing, model logic handling, and post-processing, as well as broadcasting the input to multiple models to form an ensemble. That's what I mean by multi-model inference. And then by building on top of Ray and we're having this kind of native API, you can write arbitrary Python code and integrate arbitrary Python libraries to serve model and sort of provide you a perfect mix of writing business logic with your machine learning model inference code. And in particular, the deployment graph API I'm going to introduce today is going to be focused on this kind of multi-model inference support. Cool. Throughout this talk, we're going to be walking through this example of a simple content understanding application. So let's say if we want to take an image, given an input image, we want to say put it through a machine learning application that will give us some combined feature output of, say, for example, what is a category, what are the objects, what are the bounding boxes that can give you some tags about this image. So on high level, this might look like a simple application, but if we really want to make sure to see what a simple app could look like in production, it actually turns out to have a lot of moving pieces. So the first piece we typically see is the image sometimes are like big enough, you don't want to just send them around. Sometimes you might want to just put them in an object store and retrieve it later. So that's easy for download and easy for fault tolerance. So when an image comes in, we might need to download it to retrieve it from an object store. And then after we get an image JPEG, we typically sometimes need a pre-processing logic to turn the JPEG into a tensor format that model are trained on understood. And after the preprocessor, we probably want to send it to a lot of image classifiers. And the reason being is typically you don't want just one image classifier for the end-to-end application. Sometimes you want to fine-tune each classifier for each category. Or sometimes you just want an ensemble of them to improve the output. And of course, as I shown before, maybe our application doesn't just want a simple classification. Rather, we also want some sort of image detection with bounding boxes and sort of point cloud, a kind of output to help us tag the image furthermore. So the pre-processed image, we also want to send it to a different model, and in the end, combine them together for our final output. So this example kind of might seem contrived, but it's our best attempt at capturing a lot of real machine learning end-to-end application when they're running in production, what cases they might run into, what they could look like. And let's think about how would you build this today, right? And as a preview, if you just want to build this today, there can be a very simple solution. You can just pack all the logic together and put them into a single container. And this container will essentially run the for loop, run the if statement, run all the logic in like a single sequence. And then you can use Python to write it. And then you can pack all the application into a single container and scale that as a standalone scalability unit. Of course, this approach is actually fairly easy to write and develop and operate. However, it is unable to scale each model independently. Essentially, each container here is doing the first thing and the second thing and last thing like all together in sequence. And additionally, because of this architecture, it has high latency and as well as low throughput and is fairly costly because when it's processing one thing in a container, actually all other parts are idle, and additionally, you don't have all the right cache efficiency to help you to optimize the latency as well. So a lot of people look at this, it's like, well, we can do better. A better approach here is to split each individual pieces into their own component, into their own container. So you can imagine you can have, any of you can write this kind of scenario where you can put the TensorFlow model in their own container, PyTorch model in their own container. Maybe you have another web application fast API to orchestrate the request in like essentially the microservices style. But this approach, of course, requires a lot of care in operating and deploying them in production. So that's why right here we're putting the Kubernetes icon as well as a lot of YAML icons right here because we will have to write all that. And this approach gives you the advantage of scale each individual models independently using different resources. It's very easy to configure and typically can reach an optimal configuration. However, it does require you and your team to have deep understanding of how to orchestrate and operate this kind of application on Kubernetes. So Reserve is coming as a sort of intersection of these two approaches, and we are a framework built for multi-model inference. We're kind of in between here in the way that if you look at where Reserve fits, you can put all the models in their own container, but Reserve helps you to pack, say, both the TensorFlow and the PyTorch model or some of the business logic in one node, and then all the other in other nodes, or however you want to scale them and flexibly place them. And just to compare it for this image, if you compare this one with the previous one, you can clearly see the efficiency gain we're providing here. Now, let's take a look at how would the previous app, to further enforce this idea, how would the previous app to be placed on Reserve? For example, typically Reserve can be run on top of Kubernetes. On top of Kubernetes, there can be different Reserve pods. Essentially, you can imagine these are the standalone units of scaling. And within Reserve pod, we can maybe put the downloader in one of the pod and the preprocessor on the other pod to balance out. Or maybe the first pod can fit all the image classifier well, and then therefore we put the other model into another pod to balance it out. And in the end, we can run a combined logic somewhere. And the key here is the flexibility and efficiency of the placement. For example, if we say each pod has 1 GPU and 4 CPU, and we're actually assigning, say, each image classifier to only use 0.3 of GPU. And in this case, Reserve will help you to only use 1 GPU for all the 3 models when you are running in production. So that's sort of a picture about what Reserve is, what problem are we solving, and where do we sort of stand in different possible solutions for multimodal inference. Now I'm going to give you a little bit more about the context and motivation about the API. So again, take a look at this architecture. Imagine how would you write it in code, right? So let me just quickly go here. So if you want to write it in code, it's a little bit tricky, right? We get the architecture right, but the API to compose everything together is going to be it requires a lot of deep understanding and expressiveness. So before I dive into the API, there's actually a lot of different trade-offs you want to think about here. Do we want a declarative API, or do we want an imperative API? So declarative API, for those who don't know, is essentially like some sort of API that provides you what the desired end state or goal state will look like. So example of declarative API are like SQL, essentially, where you're describing what the output data do you want it to look like, but you are not writing the for loop, the if statement, the threading, or other things to make it happen. So typically, when we're describing the declarative API for this kind of use case, we find declarative API is very good for production because it's very clear to see what's going to happen actually running in the final architecture. But then also but the downside is sometimes not very flexible. It's hard to express what you want to do with a sequence of declarative API and YAML. On the other side, there's imperative API. just like a programming language where you can provide step-to-step instruction to show how to reach the end goal. Like Python, Java, any programming language is imperative, as in you can tell us exactly what to do. So they're easy to use, but a lot of cases they're hard to program because they're so flexible, and a lot of cases they're error-prone. So judging between these two, we can take a look at some of the clear examples. We don't need to read the code here. So SageMaker has this kind of API that's give you sort of like the trainer interface, the inference endpoint interface, and then you can just orchestrate them in their Python DSL. So SageMaker is declarative. There's also there's a framework called kserve, which allows you to write YAML configuration format in like kind of a Kubernetes native style. Again, right here, if you want to compose different models together, you're just writing like configuration lines in the YAML format in their DSL. And DSL stands for domain-specific language. And in this case, again, you can see it is very declarative. On the other hand, a great framework for model serving typically is like we found is BentoML. So you might have heard of BentoML. BentoML's model composition API is very flexible and very powerful. You can see essentially you are defining your Python logic in there using code and orchestrate the computation and communication yourself. So we can say that BentoML, on the other hand, is on the imperative land. So, and let me just put them in the sort of map right here. We have declarative and imperative, and then we know SageMaker, BentoML, and where does other things stand, right? RateServe 1.0, which is the version that we have been out there for the past 2 years, are actually on the imperative side. We are allowing you to have the flexibility of composing different models together using Python code. However, this comes with several challenges. But before I dive in, let's do a quick review of the RateServe concept for those who are not familiar with RateServe. So in RateServe, our core concept is called deployment. A deployment essentially is a collection of what we call replica, where each replica is a process of instantiation of your model. And in this case, you can, if you know Ray, essentially each replica is also a Ray actor that can communicate with each other. So as you can see right here, we're instantiating a model class decorated with serve.deployment, turning the model into a serve deployment, which can now be scaled into different numbers of replicas. So, and the other concept in RateServe is called serve handle. Serve handle essentially is a client that allows you to call a deployment in Python. So as I mentioned before, we have deployments that have replica. Serve handle is like an object that lets you basically getting the input and send it to another model, get the output back, and send it to yet another model to perform this kind of composition or calling them in Python. Essentially, it's a client-side load balancer that will direct the request and load balance them across different replicas. And the important thing here is with deployment and with serve handle, you can build arbitrary complex application. For example, right here, you can have an orchestrator that calls the first model and the second model, all using these two simple API. So right here, I'm trying to walk through the how would you actually implement it in 1.0 API. Essentially, we can have an orchestrator deployment that will get the serve handle to the first model and second model. And in a block, essentially, you will be able to perform this kind of chaining operation using a handle.remote API or ensemble operation using handle.remote API as well. So it's infinitely flexible. It's very imperative. Now, it does come with a lot of challenges because, as I mentioned, as you might have seen before, because we're creating the serve handle using our Python code in our init function, so serve doesn't know which deployment to start first, and how do we manage the dependency between the two. There's also implicit data flow across deployments. In this case, it's hard to read and debug and understand what's going on because everything is written in code in this imperative API. And the complexity will just grow as your application is getting more and more complex, and you start adding more and more stages. And lastly, the core of the problem here is that we have no high-level graph abstraction. We haven't been able to tell you, well, what the inference call graph actually looks like, what components does it have, because everything is just serve handle and deployments to us, right? So we cannot deploy these as a unit. Now, so these are all challenges come from a purely imperative API. That's why in RateServe 2.0, we want to make sure to build an API that's essentially the best of both worlds. That's essentially give you the expressiveness of imperative API, as well as give you sort of the good for production side of a declarative side. So let's take a look at exactly what does it contain of. So again, just to recall, we want to evolve our imperative API to declarative side, and we have two main problems to solve, basically implicit dependencies and implicit data flow. To solve the implicit dependency and data flow, we have introduced a new API on deployment called bind. Bind, essentially, you can be called it on the deployment class constructor, as well as calling on the deployment class method. So when you call it on the constructor, you are using it to define the dependency among deployments. I'm going to show you more example later. And when you call it on a method, you are kind of declaring the data flow dependency of what would it look like. So on the right, I'm showing an example of essentially the class deployment A, which you can call the bind on the A itself, as well as on the sort of the predict method itself. So these will be the two main concepts where the single API help us to build an end-to-end deployment graph. So let's take a look at bind on constructor. Bind on constructor help you declare dependency among the deployments. In particular, will inject the serve handle at runtime. So take a look at this example where the orchestrator depends on model A, deployment A, and deployment B. In our API, you can just specify orchestrator.bind, A.bind, and B.bind. In this case, in our actual init function of the orchestrator, we're not giving you the deployment as the name anymore. It's not anything else, rather just the handle that you can directly use to call the models. So the init method bind helps you to create this kind of dependencies and be very much easy to see and visible. Bind on method call help you to make the deployment, basically the data flow explicit. And in particular, we're using it mainly for you to declare the data flow, what would it look like, also to avoid this kind of async await messiness in your code. So example here is you can have model1.bind, model2.bind to create them, and then declare this using this input node context manager to essentially build your graph like a declarative way like this. And in the end, you can run the whole thing just like how would you run all the deployment together. And I'm going to start showing you a sequence of example of building the deployment graph from with this kind of data flow API. So the first one, of course, is chaining. You can declare the models, model 1 and model 2, and our graph are essentially 3 lines. You declare the input node, you pass the input called m1.forward.bind, and then you pass the input to m2, called m2.forward.bind. Essentially, each call declares the edges and help us to understand the data flow relationship. And just like chaining, ensemble is not too different. Essentially, the input is getting passed in from the input node context manager and getting to passed into M1 and M2 at the same time. And once it's getting to the M1 and M2 at the same time, we can pass the output to our average combined node that will essentially declare the last edge in our data flow graph. And then, of course, with these two primitives, you can very easily just start building arbitrary graph together. So right here is an example of getting our ensemble together with our chaining, and then combine everything together at the end, right? And then this does scale to the cases of hundreds of models chained together or ensemble together or arbitrary complex graph. And then, of course, I'm just here showing you as an illustration example, you can build a tree of models in very simply just like 4 or 5 lines of code. I'm not sure who actually do this in their end-to-end business app, but just here as a demonstration of you can use this API to build arbitrary graph that's kind of, it's a very expressive API. And then, but however, we typically, this is sort of give us a base case of what the data flow look like. But what happens if you have dynamic selection, in particular what we call the dynamic dispatch node in your use case? So example right here is we want the input to come in, and then we want to make sure the input goes to model 1 or model 2 given a random number or like given some random selection. Of course, it can also be given some, it can be used to select based on the input attributes or the input categories or any other features like that. So right here, we're not doing anything different. All you need to do here is instead of declaring the data flow, you can fall back to the deployment on constructor approach where you can start using the code to express the data flow program where, for example, right here, we implement a random selection deployment. We take the other model as dependency on constructor, and in the call method, you can now start essentially choosing exactly what to do. So this is how we have this dynamic selection mode where it allows you to embed the imperative API call as part of the declarative data flow. Now, this really goes with the principle of Ray, where we want to make sure the simple things are very simple, and we're making the complex things possible. So you can start simple, start easy, and then go beyond that to make your actual business application more and more complex. So this is essentially the two API we had in mind to help you to build the end-to-end application with both the declarative front as well as the imperative front. And we'll help you to, we hope this API can help you to do that. So in the end, let's wrap this together by taking a look at our content understanding application again. So with the content understanding architecture, it's very simple that we just need to declare every single component as their own deployment, and then sort of start calling, binding them, creating their constructor, right? So for example, our dynamic dispatch node depends on the classifier. So we had this dynamic dispatch.bind star classifier to inject the dependency. And then we can declare the declarative data flow with input node program, where we pass the input into the downloader, pass the output from the downloader to the preprocessor, pass the output from the preprocessor to both the dynamic classifier dispatch as well as the image detector at the same time, sharing the same input. And in the end, getting the both output while piping them to the combined node. So this is really how you can build this kind of real-world looking end-to-end machine learning application with this few lines of code. And in the end, we have this new API to help you essentially run an application very easily, a whole graph application very easily. Because with the bind API, we now have a concept understanding of what a whole graph looks like. You can use serve.run, which is a brand new API we introduced to help you to essentially deploy everything at the same time and start orchestrating the data flow. And the DAG driver you see here essentially will help you to most efficiently orchestrate the data flow with high throughput and low latency. Cool. So that's sort of the walkthrough of the API. I understand that's a lot of code. And a little bit preview of what's coming up next. So on our roadmap, we're going to make sure that with the deployment graph, we can have much better autoscaling. And the reason I'm mentioning here is because Serve already supports really, really good autoscaling based on the incoming request load, as well as scaling to 0, where the traffic, when your model is not receiving any traffic for some duration of time, we make sure to deallocate the model properly and only bring it back up when the model comes. However, this autoscaling algorithm of individual autoscaling in particular can run into inefficiency or sort of unoptimized scenario when it's running in a graph. For example, when requests come in, we want to make sure it's autoscaling both the node in the beginning as well as informing the autoscaling for the nodes that's going to be ready later on. So we're going to be actively working on that, as well as making sure to add more graph primitives to help you to write sequential node, write ensemble combining node, as well as if you squint at it, this is exactly the primitive we need to write A/B testing and perform live model inference A/B testing and switching at the runtime. And additionally, as you can see, with this declarative API, it can help us to do a lot of performance optimization under the hood. For example, if we want to combine preprocessor and the downloader together, where we will immediately avoid a copy, or we want to scale out things differently or co-place things to optimize both the downloading network bandwidth as well as the resource, CPU, and memory utilization. And we're also actively working on visualizing the graph to help you understand what's happening in the application. And this is really the next step here to make sure that you can debug, observe, and what's going on with this kind of very complex, messy pipeline. And lastly, in the end, we're more than eager and happy to talk to you about your suggestion on the sort of the multi-model inference use case. And in conclusion, this talk I covered how the Serve model composition ability is really built to be powering the most crucial part of your business application. And our Serve is uniquely positioned as this kind of framework to do that kind of job, as well as in the Ray 2.0, our sort of API is trying to make sure it is both has an imperative front as well as declarative front to make sure that you have the right API to build complex application. And you can try it out today. That's our documentation page. It's Ray 2.0 has been released. So even if you just open a laptop right now, you should be able to try it. All right, with that, I'm happy to take any questions. And Dimitri will be running the mic. So.
Hello.
Yeah.
Thank you. Yeah, very exciting development. So I'm thinking. I know this might be like a little outside of this, but I noticed that when you have like dynamic graphs, but I'm wondering if, let's say, in the for loop, you kind of can control how many nodes you create on the fly. It's like it depends maybe on another node. Is it dynamic? Is it as dynamic as that?
Yeah, exactly. So there's two both are programmable, right? Like in the graph data flow declaration layer, you can use for loop, as I showed in the tree example. You can use for loop, you can use if statement to dynamically sort of create a data flow once and then deploy it in. But also, to actually massage the actual data flow, you can use a dynamic dispatch node, which we believe will cover the rest of the things that the declarative data flow that doesn't cover. And in there, again, you can use the for loop and all other things, and essentially as a fallback to all other things that the declarative data flow cannot do.
I know you mentioned that for auto-scaling, there's like work to be done, but meanwhile, is there tooling or like is there an API exposed to kind of look into the data flow? Like for example, there's an inference graph which is composed of multiple nodes, and you need to, as a developer, you're trying to look for optimizations of maybe there's like data backup in one part of the node and not in the other one.
Yeah, so this is a great question. So essentially in Ray, we'll provide various tooling for you to observe the performance as well as observe the shape of your program. So observing the performance, we have built-in metric collection, Prometheus metric exposition, as well as there's a way, for example, you can benchmark against your Ray program on a Kubernetes cluster to see what how your application perform and drill into the bottleneck, as well as a way to essentially visualize the graph, right? So we said we're already working on visualization, but like we're already, both for auto-scaling and visualization, there's already primitive support in Ray 2.0. So you can already get started with that, and we want to make sure the experience is the best class. Yeah. Any question?
Any thoughts about coupling these kind of workflows back into train, where like you can make a dynamic selection and say like, hey, I have my control, I have my future is now below control, I want to kick off a retraining pipeline, like stuff like that.
So yeah, so there's two parts. One is that the Ray serve, by running on top of Ray, we actually have native integration, and you can totally just kick off a training job from within a Ray serve pipeline and actually complete the loop that way. But and yet another thing is this kind of declarative API is actually not just a Ray serve API. It's actually a Ray core layer API. If some of you, if I've been to the Ray workflow talk about the Ray workflow engine, it's actually already, we're using exactly the same backbone, and we're more than excited to bring that kind of, this kind of declarative construction API to more library like train and dataset and others.
Quick question on, so in the example, presumably the endpoint you expose is just like one to do the whole thing. What if I also wanted to expose a sub part of that graph? Like, could I do that? How would I do that? What would it look like?
So that's also very much possible. We have the primitive essentially to support different entry points to the graph and expose them under different routes, as well as go beyond that, where you can bring in different DAG to form if you want to think about it, essentially a different entry point is just a matter of bringing a bigger graph and creating more edges for your application. So we definitely have support for that. We'll have published pattern for that, and we're more than excited to work with everybody to see what you build with it.
I think we're out of time for questions, but we can continue the discussion in the lobby and elsewhere. Thanks, everyone.
Thanks, everybody.